Okay, so I want to start with a recording of problems 21 and 23. In 21, it says you have a door, and the door is going to be closed by a door closer that's attached to the top of the door frame. They tell us that the width of the door is 0.91 meters. Its height is about, I think, 2 meters. And then it has a thickness, which I'm not going to draw right now, which is 4 centimeters thick. Okay, so then it says the door closer puts a torque on the door. That's equal to 5.2 Newton meters. So we want to know what is the least force that you need to apply to the door to hold it open. So we know that if you put a force on a door to cause a torque that would counteract the door closer, that you would, if you want to put the least force, you would want the largest R, right? Distance from the hinges, which are maybe over here, right? And so we want our R value to be as large as possible, which would mean R would equal 0.91 meters, right? Okay. So let's go ahead and do some of the math then. We can say that torque is equal to RF. If you want the minimum force, then you would want to use 90 degrees, right? Because then you get the most out of it, right? So out of that small force. So let's go ahead and plug in what we know. We know that torque is 5.2 Newton meters. Direction we're not really worried about. We know it's going to counteract the direction of whatever way the door closer is going. R is equal to 0.91 meters. F is what we want to know, and sine 90 is just 1. So we can go ahead and do the math then, and we can see that F equals 5.2 Newton meters divided by 0.91 meters. Meters are going to go away. We're left with newtons, which is what we want for a force. I think it's around 7 or so. Let me see. 5.2 divided by 0.91. Oh, no, I guess I'm wrong. 5.7. Yeah, that makes sense. It doesn't go in there. It goes in there, goes in there at least 5.2 times, but a little more than that because it's smaller than 1.91 is. So 5.7. I'm going to go with 714. Okay. Anyways, good. Let's go ahead and go to the next problem. Number 23. This one's a little tougher. We are given a circle, which we say is a merry-go-round, and then we're going to go ahead and put a couple forces on it. We got one from Tom and one from Jerry. So Tom puts a force that looks like this. And I'm going to go ahead and dotted line that back. He does it at about right at 9 o'clock there, or the negative x-axis. And so I'm going to dotted line from here too. And then I'm going to go ahead and put an angle right here of, this is 60 degrees. All right, and then we'll do another one. We'll do Jerry's force, which is going to be at a sharper angle, almost at 90, but not quite. So maybe something like this. I think Jerry doesn't have as much force. I can't remember. Yeah, Jerry pushes with 35. All right. So then we can go ahead and dotted line that back. All right, and dotted line that over. And we got another angle there. And this one's going to equal 80 degrees. All right, so this is F, Jerry. And that's equal to, I think they tell us 35 newtons. And force Tom is equal to 50 newtons. All right, so both Tom and Jerry are going to put a torque on this merry-go-round, right? And we're going to find out what the net torque is. They're pushing in opposite directions. Looks like Tom's pushing in the positive counterclockwise direction and Jerry's in the clockwise negative direction. And we want to know who's going to win out here. Obviously, their angles matter because they didn't push at 90 degrees. Had they pushed at 90 degrees, they would have done more torque, but they didn't. And so Jerry's closer to 90 degrees, right? But he's got less force. And Tom is further from 90 degrees, but he's got more force. So it'll be interesting to see who wins out here. So what do we want to do here? Well, we want to find torque for both of them, and torque is going to equal, right, R times F perp. Well, we know R. They tell us that for this circle, R is equal to, or diameter is equal to 3 meters for this merry-go-round. So we know the R value is 1.5 meters for both Tom and Jerry from the axis of rotation in the center. Okay, so all we got to do is get F perp then. And yeah, and then we should be good. So let's draw some vector components here. And so we can see that, I'll draw the first one straight down. So there's F perp for Tom. And we can do the same thing for Jerry. And that's F perp for Jerry. All right, and both of these create 90-degree right triangles. And the question is, where is that 60 degrees? Where is that 80 degrees? So the 61 is kind of easy to spot out because this is 90. Therefore, this has to be 30, right? Because you have a 90-degree angle here. You have to have 30 here because this is a straight line. This blue line, the dotted line, has to total up to 180. So 30 plus 60 plus 90 is 180. Anyways, long story short, our 60-degree angle is down here in the bottom right of this triangle. And that's important because that means that F perp is an opposite and force Tom is a hip. Okay, coming over here to Jerry, let's see, where's that pink angle? I think the same logic can apply here, right, which is going to put this pink angle in the bottom right corner. Just make sure that you're convinced of that 80 degrees is down there. And because that's important, right? Because you get that wrong, then screws everything up and makes the whole problem wrong. And that actually happened to me. This is the second time I've made this video. So yeah, be careful. F perp is a opposite, and the hip is that 35 newtons. All right, so now we can say then that the torque caused by, doesn't matter who we go with first, we'll go with Tom. Torque caused by Tom is equal to R, which is 1.5 meters, times F perp, which, what is F perp, right? And I think for both of them, we can just use sine theta equals op over hip, we can then say for both of them, sine of theta is equal to the opposite, which is F perp, over the hip, which is F. And we can say that F perp is equal to F sine theta. So we can go ahead and say then that that F perp for Tom is going to equal 50 newtons, right, times the sine of, what's this angle? I think it was 60 degrees, yeah. And then the torque of Jerry is equal to 1.5 meters times 35 newtons times the sine of 80 degrees, not 38. Ugh. Get out of there. Okay. 80 degrees. All right. Good. So now we have to remember that torque net, which is what we want from this problem, is equal to the sum of the torques. That means that torque net is equal to the counterclockwise torques. So that's going to be torque Jerry, right? I know, torque Tom, sorry. Torque Tom first, right? The counterclockwise torques minus the clockwise torques, torque Jerry. So we can say that torque net then is equal to 1.5 meters times 50 newtons times the sine of 60 degrees minus 1.5. I'm going to run out of room, dang. I'm going to write this below it, minus 1.5 meters times 35 newtons, still might run out of room, sine 80. Whoa, that's close. All right, and then we can do some math there, right? So we end up getting 1.5 times 50 times the sine of 60. Sine of 60 is that nice one, right? I think so. No, that's the 0.866 here. Okay, so 64.95. Whoops. Okay, and that's going to be Newton meters. And then we're going to subtract away from it the other one. Which is going to equal 51.70 Newton meters. All right. I'm just going out 2 decimals, and that's fine. So now I'd subtract those two. We get 13. That's an equal sign. 13.25 Newton meters. All right. What direction is it? Positive direction. So you can say positive or you can say counterclockwise. All right. So that means that even though Jerry had a better angle for torque with the 80 degrees, that Tom's force, even directed at a less optimal angle, actually exerted more torque. So because 60 degrees is obviously less optimal, right? Sine 60 is smaller than sine 80. Okay. All right, so anyways, part B. So in part B, the question is, what is the net torque if Jerry reverses the direction he pushes by 180 degrees without changing the magnitude of the force? So all he's going to do is take that green arrow, right? And maybe I'll use red. Red stands out pretty good. Yeah, we'll try it. All right, and he's going to flip that force to point this way, right? So when he does that, it's still, a force of 35 newtons, right? But does it change anything? Let's draw some vectors and look. All right, F perp Jerry now points this way, and it's still opposite that 80 degrees, right? So it's still going to equal 35 35 sine 80, right? That's still going to be what it equals, because it's no different than being in the purple vector down below, right? So it's the same situation. So with as far as how much torque Jerry does, but one thing changes, right? Now he's pushing this way. So by pushing in this direction, right, the torque is going to be this way, right? And this is counterclockwise, so this is positive. So really all I have to do then, if we're exerting the same torque, right, because R is still the same, this is still the same R value as before, and all we have to do then is take our sine from here and add it, right? So I'm saying our net torque this time is still the sum of the torques, right? Which we said before. But this time we are adding because both torques are counterclockwise. All right, if we add those two, give me 1 second for the calculator. We get, if my math is right, 116.654 Newton meters. All right, so be sure to check those answers with the back of the book and make sure we didn't make any mistakes, but they should be right on. All right, that's it. Enjoy the rest of your weekend. Hopefully you see this video in time. All right, take care.